So after examining the two tracks that nor'easters typically take, we want to answer the question, why is the East Coast favored for this unique cyclone formation? It really all has to do with the Gulf Stream current. And so the Gulf Stream current is the transfer of warm water out of the Caribbean. It tracks along the East Coast, again, just south of the 4070 benchmark, and goes up into the poles. And so water or ocean currents are very similar to air currents, where warm water wants to move north to cool, cool water wants to move south to warm, just like air does. And so with nor'easters, what you have is you have this intensification or this drastic temperature gradient between continental, polar, or even Arctic air coming down from Canada, and you have this warm, moist fuel source for these nor'easters to travel along that create this very unstable atmosphere. And so what this is it's called a baroclinic instability profile. And so what baroclinic instability is, it is the unstableness of our atmosphere based off of two very different air masses colliding with one another. So here what you have is you have warm air that's traveling north because you have the warm air that is traveling with the Gulf Stream current, and you also have this cold continental air mass that's coming out of Canada, or it could be a very dense Arctic air mass that comes out of Canada. That also happens as well. And so here you have this nice frontal boundary that develops between the two. So Mother Nature likes to be even. And so when Mother Nature is not even, it creates these intense systems. And so that's essentially what baroclinic instability is. So when we look at these tracks here, what kind of track do you think this system is going to be based off of this surface map? Well, just by looking at this would be a track C, or a Gulf of Mexico track, simply because here is the area of low pressure that not necessarily is developing off the coast of the Carolinas, but is tracking just along the East Coast, number one. And number two, there really is no parent area of low pressure, so this is the only single area of low pressure that is on this map. But here again, you have this area of high pressure that is out west of the Great Lakes, and we also have an area of high pressure sitting right over New England. So basically almost positioned right in the Canadian Maritimes. And remember that the presence of that high pressure system is a key signature feature when we talk about intense snow, because we have a lot of moisture that is traveling into an area that has a very cold air mass. So this high pressure system denotes, especially for the wintertime, it denotes a cooler air mass. And so if this is the winter, then this would be a maritime polar, or a continental polar air mass, or even an Arctic air mass that spins clockwise. And so all of my cold air is now pooling from the north. And so now what I have is I have all this moisture going into a very cold environment. So to show an example of what I'm talking about here, I'm actually in my backyard. I have a cup full of boiling water, and outside it's very dry, but it was also very cold on this day. The temperature outside was -8 degrees Fahrenheit, so it was still very cold. And what I did is that I took a very hot substance, hot water, and what I did is that I threw it into the air into a very cold environment. And so what this did was it created a snow cloud instantly, simply because the air cannot hold that moisture. The air is so cold, the amount of moisture it can hold is so little. And I'm putting a very warm substance with a lot of moisture into a very cold environment. So essentially, I'm taking a gallon of water and trying to fit it into the cap that closes the gallon of water. If you can think of that analogy, that's basically what I'm doing. And so here you can see how it basically just falls as almost like a giant snow cloud. So when we talk about the moisture source for nor'easters. And when we talk about why New England gets so much snow, or even parts of New York and Pennsylvania, even Manhattan, this causes a huge problem as well, especially for the track B storms, is that where does all this snow come from? Well, it comes from the contrast between a very intense area of high pressure that is bringing in some really dense cold into those areas, and we have a lot of moisture being fed in off the Gulf Stream current that collides into this very cold air mass, and just like the video I just showed you, creates a baroclinic instability atmospheric profile that causes an intense area of snow. And so here you can see as this system develops, this is very tightly packed, and here's all the moisture back in through here. So this scale just denotes how much moisture is in the atmosphere. So the darker the colors into the blues, it means that this is the liquid equivalent of the amount of moisture in the atmosphere. So this would be in inches. And so here you can see back in the more tropical locations closer to the Caribbean, you can see that the amount of moisture, if you were actually to wring it out like a sponge, the amount of moisture that you would actually be able to wring out of the atmosphere would be about 1.5 inches of liquid precipitation. So if you would actually measure it, it would measure 1.5 inches in some sort of beaker. But here you can see that it's not necessarily that story up in through southern New England, although you have 1 inch to 1.5 inches of liquid precipitation. Well, if we look at the 10-to-1 snow ratio, for every 1 inch of rain is actually 10 inches of snow. And so that is based off of temperature. So the colder it is, the higher that ratio can be. And oftentimes that these nor'easters or these snowstorms can easily be a 20-to-1 ratio. So meaning to say that if this was 1 inch of liquid precipitation that was squeezed out of the atmosphere, it would actually be 20 inches of snow. So you can see how things can pile up rather quickly, and oftentimes these systems do make national headlines just because it impacts so many entities and really causes a lot of hazards, especially on roads. So just to get a little bit of a better idea, now we're just looking at the temperature profile within a typical nor'easter. Again, this would be a track C. This is the same storm system. But here, you notice all these colors indicate 850 millibar temperatures, and this is in Celsius. So 0 degrees would be freezing. So here in this almost turquoise-like color, this would be the boundary between below freezing temperatures at 850 millibars to the north and warm air above freezing or very much above freezing towards the south. So this is that baroclinic instability almost path that these low pressure systems end up taking. You can also denote here's the trough, and here we have a little bit of a ridge out in the Atlantic Ocean. So here you have a little trough. Okay, if we cut this trough in half all the way into Louisiana, you know that our area of low pressure should be on the right side. Our area of high pressure should be on the left side. This, even though there's no H on it, this is an area of high pressure. So all of my cool air is following this low pressure system, and you can see the outline of the jet stream based on these temperatures. And here you can see how this low pressure system is going to just track just south of New England, and we have an area of high pressure just north of New England, just about 24 hours before this low tracks just south or impacts New England. So here all my cold air is locked in place. I have the perfect setup. I have a lot of moisture. I have cold air in place in southern New England, even back through Pennsylvania and New York State and Manhattan. So I have the perfect scenario for a very well developed nor'easter. So I have plenty of cold air, plenty of warm air, plenty of moisture. And so watch how this system develops. Now just in a couple hours time, 12 hours time, here you can see how this area of low pressure really developed. So here it went from a 1012 millibar low to 1004 millibar low. And then again, it bombs out into the Gulf of Maine and continues into the Canadian Maritimes as at 996 millibar low. So here you can see how the frontal patterns are drawn on this map. So here would be the warm front. So warm air is moving north, cold air is trailing south. Again, here is, if you notice my mouse, here is the trough. The trough axis is right in through here. So basically the border between Georgia and Alabama, that's where the trough axis is. Cut the trough in half. The right side, here's the area of low pressure. The left side, area of high pressure. So here you can see how the jet stream moves. Here's our area of low pressure tracking along the jet stream. And so as the storm exits and really bombs out into the Gulf of Maine, here we have a very, very well-defined circulation, and eventually this storm will go under occlusion and then therefore will dissipate.